In this problem, we're going to look at the energy consumed while burning gasoline, and burning gasoline as we're driving a car. We're going to make some reasonable assumptions, and what we want to find out, what we're going to calculate in the end, is the rate at which the car is using energy. The rate is... So we'll make the problem a little more definite and put in some reasonable assumptions here. We'll assume that a car is moving at 60 miles per hour. And how much gas is it burning? Well, we'll assume it's burning gas at a mileage, at a rate determined by a gas mileage of 30 miles per gallon. And we want to know, what is the power consumption in watts? Recall that power is energy divided by time. So what we're going to do is make some... We're not given a specific energy or specific time. We just make some assumption that allows us to calculate. We just can assume some particular distance or some particular energy or some particular time, and we calculate the other one, and we get their ratio. Let's see how it works in this problem. This problem, it's convenient to just assume a particular distance. Then we calculate energy for that distance and the time for that distance, and we divide and we get the power. In the end, it doesn't matter what we assume for that distance or for that time. We're going to get the same thing when we calculate, when we do that. So when we get the same thing for power. It's convenient to assume 30 miles because in 30 miles, that corresponds to exactly 1 gallon of gasoline. So I'm going to assume 30 miles, and then we're going to do two calculations. One, we're going to find the energy that's contained in that 1 gallon of gasoline, and the second calculation is the time it takes to burn that 1 gallon. So energy content of 1 gallon of gasoline, that's the first calculation. We'll use octane as a representative of gasoline. Gasoline is a mixture of hydrocarbons, 7, 8, 9 carbons, and we'll assume octane is a representative. A lot of it will be octane, but it'll be a mixture. In the end, it won't make much difference what we assume because the energy content per unit mass is fairly close no matter what we assume. But we'll take octane as a representative of gasoline. Here's an equation for the combustion of octane. Again, combustion involves a reaction with O2 to produce CO2 and water. Now notice how we balance this. We use a fractional coefficient in front of the oxygen, 25 halves or 12 and a half. We didn't do that before, but it's pretty common to do that with combustion reactions. And the reason we do it is that when we do that, the heat we get for this reaction corresponds to exactly 1 mole of the thing we're burning. And then the delta H for this reaction is called the heat of combustion of octane. If we balance it with 2, then it's easy to make a mistake, and it's easy to forget that the delta H actually corresponds to 2 moles of that substance instead of 1 mole. I won't demonstrate this for you here, but I did it before. We use tabulated heats of formation. We can find them in a table, and we do the products minus the reactants. And we get for this reaction, delta H is minus 5,470 kilojoules. It's exothermic, as we know it must be. So that means that 1 mole of octane can supply us with 5,470 kilojoules. So that gives us this equivalence relation, which we can use in conversions. Here are some other conversions we need to solve the problem. First of all, the heat of combustion gives us the energy in 1 mole. We need to convert moles to more convenient units. And the molecular weight of octane is one thing we're going to need, and the molecular weight of octane is 114.1 grams per mole. So that gives us 114.1 grams is equal to 1 mole. We need the density of octane, and we look that up and we can find that it's 0.703 grams per milliliter. Because we measure gasoline in volume, not in mass. But the volume unit we use is not milliliters but gallons, so we look up a conversion between gallons and milliliters, and we find 1 gallon is 3,785 milliliters. So the calculation proceeds by starting with 1 gallon of octane. We use this conversion to convert gallons to milliliters. We use the density to convert milliliters of octane into grams of octane, so that comes from this one. And then we use the molecular weight to convert grams of octane into moles of octane. That comes from here. And then we use the delta H of reaction, the heat of combustion of octane that we showed on the previous slide, to convert moles of octane into kilojoules. When we carry out that calculation, we get 127,500 kilojoules, or in straight joule units, 1.275 times 10 to the 8th joules. Next, we need to calculate so that's the energy we get by burning 1 gallon of gasoline. If we're moving at 60 miles per hour, how long does it take to burn that 1 gallon? And we assumed a mileage of 30 miles per gallon, a speed of 60 miles per hour. This shouldn't be too hard to figure out without formally setting it up, but here it is formally set up. The time to consume 1 gallon. We use the mileage to convert gallon, so 30 miles per gallon. So in 1 gallon we go 30 miles. How long does it take to go 30 miles? If we're going 60 miles an hour, it should be obvious that that's half an hour. And we'll convert that half an hour into seconds, and we get 1,800 seconds. So now with the energy and a time, we can calculate the power. The energy, recall, was 1.275 times 10 to the 8th joules. The time is 1,800 seconds. So the power, we get by putting the energy over the time, and we get power in watts, 70,800 watts. Or we could say 70.8 kilowatts. That's also a common unit. To compare, recall that we earlier calculated the power consumption, the power consumption by the human body and just burning the food it does in a day, and we found a power consumption of about 100 watts. So a car traveling at 60 miles per hour is consuming energy at approximately 700 times the rate of the human body.